Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, we're going to talk about basin characteristics, parameter estimation, and coordinate systems. All right, what I have on the screen here is HMS, and I have a sub-basin that's already been delineated based on watershed. So we're seeing a number of sub-basins here on the map. As I zoom out, we have the sub-basins, we have reaches, and we have junctions all labeled in. This particular example is in the West Coast, California, on Central Coast. And if I go up to map layers and turn off the identified streams, and then turn on the terrain, you can see this is the grid that I was working with. All right, so that's not too important for today's lesson because we're going to be talking about the parameter estimation and basin characteristics and coordinate system. So let's start by going up to the parameters and then characteristics. Now we have two options here. It's subbasin or reach. This is going to give us data about all the subbasins or about all the reaches. So let's start with subbasin first. When I click that, I get a table that is actually fairly wide and has a bunch of data. So here are all the fields here as I expand out to the right side to show everything. On the far right column here, far left column, I've got all the subbasins listed down one at a time. Now these are ordered hydrologically, so that's why the sorting here on the top right here, there's a drop down for sorting. It says Watershed Explorer, which means it's the hydrologic sorting. I can also change that to alphabetical if I want, and it's just a string sort. So without zero padding, it's not quite numerically correct, but that's what you got there. I'm going to change it back to the Watershed Explorer, which is hydrologically. In the left, we do have a filter as well. So there's no filter applied at the moment. That's the default, but you can also filter by computation points or by zones. And I don't have any zones set up, so I'm just going to leave it at none for this video. Along the other columns that we're seeing here are different characteristics of the subbasin. So I'm just going to go through most of them real quick and let you know what they are and what they mean. The first one is longest flow path. The longest flow path extends from the subbasin outlet to the most hydrologically remote point upstream. This is significant because it's typically used to determine the time of concentration of the subbasin. So with our units of US customary, the unit system for the longest flow path here is in miles, and all the other units are listed as here as well. Then we have the slope of that longest flow path. Next over is the centroidal flow path length, and the centroidal flow path length is a subset of the longest flow path. So it starts at the subbasin outlet and then it continues upward along the same path as the longest flow path, but then it stops when that longest flow path is closest to the centroid of the subbasin. So, why anyone would want to know that, I'm sure there's a good reason for it, but I can't provide an explanation. It's probably going to be close to half of the longest flow path, or maybe 40% or 60%, somewhere around that. But it depends on the shape of the longest flow path and, of course, the shape of the subbasin. And then we have the slope of that centroidal flow path. The next one over is 10-85 flow path length. Maybe it's just called 1085. What that represents is 75% of the length of the longest flow path. And it starts 10% upstream from the outlet, and then it travels along the longest flow path up until 85% upstream from the outlet point. So this is used for the slope as well. And what the user's manual says is that the 1085 flow path slope is typically a little bit more reliable because it just takes away from the edge effects of being at the sort of the edge of the subbasin. All right, the next one over is the basin slope, and that represents the average slope of the entire subbasin. Next after that is basin relief in feet, and this is the elevation difference between the highest point of the drainage divide and the outlet point of the subbasin. Next, we have relief ratio, and that is the basin relief divided by the length of the longest flow path. And then the last two here are the elongation ratio and drainage density. Elongation ratio is a dimensionless ratio that categorizes the general shape of the subbasin. So this number typically ranges between 0.2 and 1.0, where 0.2 represents a subbasin shape that's a little bit more elongated, and then 1.0 represents more of a circular shaped subbasin. There is an equation in the user's manual too that gives explanation of how these numbers were derived. The last column here is drainage density, and it is a metric used to describe the efficiency in which a subbasin is drained. It's equal to the total length of the stream channels in the subbasin divided by the area of the subbasin. So the higher number here, basically the faster that the drainage will occur in that subbasin. All right, so that is my quick explanation on what these fields are, and they can obviously be used for calculations and parameter estimation, and that's what we'll be talking about next. But before that, we got to talk about the reaches. Before we leave subbasins, let me go ahead and just demonstrate how to get data for one subbasin. So we'll just select this downstream most subbasin. All right, this downstream most subbasin is selected, and if I want just data on that subbasin, I can come up to parameters, characteristics, and subbasin, and I get the data for just that selected subbasin. So I'm going to unselect that. Next, let's talk about the reaches. So just like subbasins, you can go up to parameters, characteristics, and then reach. This is going to give me a table of reach data here. And just like the subbasins, we have options to filter and to sort. And then we have all the reaches listed in this far left column with the reach data. So the length of the reach, the slope of the reach, the relief of the reach. The relief is the highest point minus the lowest point of that reach. So the slope is simply the relief divided by the length. Sinuosity is this far right column, and this was a new term to me. What it represents is a measure that quantifies the degree to which a channel meanders. So sinuosity equals the channel length divided by the straight line distance between the beginning and the end of that channel. So a low sinuosity indicates a straighter river, typically with a higher, steeper slope. Then a high sinuosity indicates more of a meandering river, which is typical with smaller slopes. Just like the subbasin, I can go ahead and select on any individual reach on the map and then click parameter, characteristic, and reach if I want data for just that one selected reach. Right, so that's it for the basin characteristics. Next, on to parameter estimation. The expression calculator can be launched from the global basin editors. And when I first read that from the user's manual, I wasn't sure what the global basin editors meant. But I've since learned that it can be accessed in some of these parameter field menu items. Now, right now, a lot of these items are grayed out, and that's just because I don't have enough things set up in my basin and in my watershed for these options to become available to me, but there are a few. So if I click on loss and then go to initial and constant, I have a dialog box here for each of the subbasins with columns for initial loss, constant rate, and percent impervious. So these are all default values, either 0 or blank. And then down at the bottom of this dialog box is a calculator button. So if I go ahead and click that, you have a calculator with it's a dialog box that gives me a lot of different options. At the very top is the field. So this is the field that I would be calculating. So this initial loss value here that's selected is the initial loss label, and that's what we're going to provide an expression for to later calculate. Here are the variables. Right now, there are no variables in this box because down below we have grids selected, and I just don't have any grids loaded up. But if I did, then the grids would be listed. If I click on stats, now we have a list of stats variables for the basin. So we've seen these in the previous tables with area, longest flow path slope, centroidal flow path length, and centroidal flow path slope, and so on. So we can go ahead and like double click any of these values, and it pops into the expression editor down below. Also to the right, we can use these functions, so mathematical functions, as well as these arithmetic functions down here, like your typical add, subtract, divide, and multiply. Okay, we can also just type in constants. Well, not letters, but like actual numbers. I'm not going to use this as an example. What I'm going to do is head over to not the initial and constant loss, but I'm going to go to transform and then Clark unit hydrograph. Again, we have some default values in here. But if I wanted to click this calculator button down at the bottom, we can estimate the time of concentration or the storage coefficient. So let's go with time of concentration. And then down in the expression editor, I'm going to select, let's just type in 0.25. This is the example from the user's manual, and then times, say, the longest flow path in miles. So if that expression makes sense or not, that doesn't matter. I'm just showing you how this works. Go ahead and click the calculate button down here. And as you can see over to the left in the main table, let me close the calculator. Those values were calculated here, and we have 3 sig figs is the default, but I can also change that as well. So if I apply, that would save without closing, and then the close button closes. I can go to Tools, Program Settings, and then select Defaults, no, Compute, and the expression calculator precision has is a value of 3. That's the default, but it can go all the way up to 5. So I'm going to change it to 5, and it's really the significant figures. It's not the precision. So just keep that in mind. So I'll go ahead and click OK. And then let's go back to transform Clark unit hydrograph. And then let's just change the numbers a little bit and make sure that that significant figure value increased to 5. So again, I'll click on calculator. I'll select time of concentration. I'll select the stats tab. And then let's just say it's 0.35 times, and then the longest flow path in mile, and calculate. And what happened here? Okay, oops, I clicked 8 accidentally. Okay, let's try that again. Calculate. All right, looks good. So we have those values saved in time of concentration. This might not make a whole lot of sense, and that's fine. This is just an exercise in demonstrating how to very quickly create a calculation for these parameter estimations. You can also just type in numbers too, by the way. All right, so we'll go ahead and click apply and close. The last part of this lesson, I want to talk about the coordinate system. So if you go up to GIS and coordinate system, I have touched on this a few times in other lessons, but what I wanted to say here is what the user's manual says about it. Right here, right now, we already have a coordinate system for this particular terrain and basin. But if you click predefined, the two options are SHG and UTM for standard hydraulic grid and universal transverse Mercator. If I select UTM, I do have to put in a few other values, but I'm going to click cancel out of that and just show you what the user's manual has to say. I'll leave a link to this particular site, but it's under Geographic Information Systems and Coordinate System Reference. The SHG grid is shown here and discussed first. It gives you some of the details, such as the units. The datum is NAT 83. The first and second standard parallels are at 29.5 north latitude and 45.5 north latitude. And then this central location of 23 north, 96 west is also used as sort of a datum point, sort of a 0, 0 location on a coordinate system. Down below, it mentions that 2,000 meters is the default cell size, but that uh, it will support everything from 10,000 meters down to a 10-meter cell size grid. So that's like the length of one size of a square-shaped cell. So you can go ahead and set that. And then further down, it talks about how an IJ, like a integer index, is used as well in case you're not into like northings and eastings and like huge numbers. Then there is an equation for the I and the J based on the northing, easting, and the cell size. So just keep that in mind. After that, it provides a couple examples here. Here's one West Coast example where it provides what would be the northing and easting values, and then how that converts to an IJ coordinate system with a second example here on the East Coast. All right, after that, it talks about that UTM grid system, which is the second of the two coordinate systems. And just like before, it gives you some basic information about units and datum, as well as an example. This example is for the island of Madagascar. So by all means, go ahead and read up on that. The cell size range is still the same. And there's also an example on calculating the I and J from both the west coast of the island and after that, the east coast of the island. So that was it for this video and lesson about basin characteristics, parameter estimation, and coordinate system in HEC HMS.